Electron spin resonance was first observed in 1944 by Soviet physicist Yevgeny Savitsky and developed independently at the same time by Brevis Blini at the University of Oxford. Electron spin resonance spectroscopy, also referred to as electron paramagnetic resonance spectroscopy, is a very useful method for studying materials with unpaired electrons, such as metal complexes or organic radicals. The basic concept of EPR are similar to that of NMR spectroscopy. However, instead of the atomic nuclear spin states being excited, electron spin states of the unpaired free electrons are excited from lower energy levels to higher energy levels while being exposed to a fixed microwave radiation, so that the spectrometer measures the transition between the electron spin energy levels.
The Epr spectrum is the absorption of microwave frequency radiations plotted against the magnetic field intensity. This technique is the only direct method to detect the presence of free radicals and to identify paramagnetic species. Essentially, it's only applicable to systems with net electron spin angular momentum, such as free radical systems with one unpaired electron, and systems in the triplet state with two unpaired electrons. This method can provide us with useful information on the molecular structure near the unpaired electron. In addition, the Epr spectral line shape gives insight to the dynamic processes, molecular motions, and fluidity of molecules.
In the presence of the applied magnetic field, unpaired electrons can move between two energy levels by either absorbing or emitting a photon of energy h nu, such that this photon energy is equal to the difference in energy states between the two unpaired electrons, which leads to the fundamental. With ESR, we are able to give information on materials that are in liquid and solid phases. In addition to the magnetic field, the ESR produces electromagnetic frequencies, usually in the microwave range of frequencies. The appropriate frequency can cause electrons to transition from one spin state to the other, and the energy associated with these transitions is expressed in the terms of the magnetic field, the Bohr magneton constant, and the G factor, a unitless measurement of the intrinsic magnetic moment of the electron. To measure these frequencies, we use an electron spin resonance apparatus.
Electron spin resonance spectrometers compose of four essential components: a monochromatic microwave source, a waveguide for guiding the microwave power to the sample, a cavity designed to ensure proper coupling between sample and the incoming wave, and a detector for microwave power to detect the response of the sample to microwave irradiation. Because ESR can analyze free radicals and transition metal compounds, there are many applications for electron spin resonance spectrometry to be useful in the world we live in today. An example of an analytical application would be that ESR is a rapid and convenient method for determination of vanadium in petroleum products and can measure and detect traces of manganese 2+ ions. A biological application includes studying the presence of free radicals in healthy and diseased tissues with ESR. The photosynthesis that has been carried out with photosynthetic bacteria, the oxidation of the bacterial chlorophyll in vitro processes produces an ESR signal. Within the study of inorganic compounds, ESR is used to study the catalysts and used in determination of oxidation states of metal. The information of unpaired electrons is very useful in different applications of ESR, such as spin labels, structural determination, and reaction velocities, as well as reaction mechanisms. Thanks to electron spin resonance, we are able to discover more about the little world among us, composed of atoms and molecules.